I'm very happy to have our speaker, Elliot, today, who has implemented a bunch of very, very efficient deep learning code, both computer vision and natural language processing with us at MetaMind. Just before you get started, some organizational things. Hopefully you all have checked your midterm. You will have hopefully your PSET 2 graded by tomorrow. You should all be in high gear now for your projects. And this might actually help you with your projects in the sense that, if you really want to implement your own more efficient implementations of these various models, then you can't really get away with only MATLAB and Python after a certain amount of data set size is after a certain amount of threshold that you cross. So are there any questions about midterms or organizational things today? No? All right, then
cool.
Take it away.
Hi, I'm Elliot. I work with Richard at MetaMind, and I'm here today to talk about efficient implementations of general neural networks for natural language processing, both on GPUs and in parallel environments. So why is this an issue? Well, deep learning algorithms are great. There's all sorts of theoretical understanding, but in practice, you need a huge amount of data in order to achieve high accuracy. So we need to be able to train on large data sets, and that means having algorithms that run very quickly. Just as an example, we have the recent sequence-to-sequence LSTM translation paper. So it was trained on a data set of 12 million sentences with an 80,000 word vocabulary. It took 10 days to train on 8 GPUs, and it's still not even like state of the art. I mean, still human-trained human-engineered machine translation systems are still doing better. And another example is just the speech recognition stuff that was discussed in the last class. So I'm going to talk about a few things. First on just how to write efficient formulations of all the expressions that you're working with, general sort of insight into how to evaluate neural nets best, and how to design networks that are efficient. Then I'll talk about CPUs and GPUs, what the benefits are of running on GPUs, what the trade-offs are, and where you might want to actually use them. Then I'll talk about parallelism, the different forms that you have. Then we'll talk about asynchronous SGD, which is sort of another form of parallelism, sort of what everyone else is working on now in terms of really scaling it up to large scales. And then I'll give a few thoughts on easy implementations and where sort of current research is heading in terms of improving performance. So just to give a general overview, so we're dealing with neural networks. They're feed-forward neural networks. They have really simple forward propagation formulas to compute activations, as well as a backward propagation formula. And this is essentially what we have to evaluate. We want to do this as quickly as possible for a wide range of different architectures. So how can we do this on the latest hardware? Well, let's talk about computation in just a general framework. So all of these things that we're talking about actually running on your computer are these computation graphs. And there's sort of two general categories of these, that is structured graphs and unstructured graphs. And the computational properties of these are quite different. So at a fundamental level, I mean, all these things, a lot of things are unstructured. And what I mean by unstructured is that we have an irregular dependency between the hidden units. So you can see at the bottom here on the right, an example of that is an RNTN. One of the great things about these things, they're really expressive. We can have all really cool models. Unfortunately, they're very cache incoherent. So typically the data that you're working with in memory, it's all over the place. So when your CPU or even GPU is trying to pull data into the registers to actually perform some sort of math, that operation can take a lot of time. You'll actually have a lot of cache hits. The workloads at each hidden unit can be highly variable depending on how many other hidden units it depends upon. So doing some sort of partitioning for parallel computation is difficult, as well as just higher memory usage because you have to store all this topological information. On the other hand, you also have structured graphs. So these things are really great computationally. And what I mean by a structured graph is where you have regular dependency between your hidden units. So an example of that would be a CNN. These things are great. They're cache coherent because you can lay out everything linearly in memory. They're easy to load balance because you can a priori know exactly how to partition all your hidden units and data among your computational nodes. They require less memory because you don't have all that topology. But unfortunately, they're less flexible. Ultimately, in order to gain high performance but still have the flexibility, we typically do block structured types of computations where you have, let's say in your neural net, we're working with hidden units that have like more than, we're not just talking about like individual neuronal activations. We have like blocks of activations, and that's where you can actually get a lot of performance improvement. But the major takeaway from this is that we're going to exploit structure to get good performance on our hardware. So one of the fundamental things that we want to do, as I was saying, is that we want to combine individual expressions into larger computational expressions. So a fundamental building block of all the neural networks that we're working with are just linear operations. So here we're computing the value of a single neuron, y, from a bunch of input values x, using just a bunch of coefficients, multiplying the values of x, so it's a linear expression plus just a constant coefficient b. Typically you have big blocks of these outputs, so you want to turn this into a blockwise operation. So we go from the operation on the left, where in your code you'd write a loop over all your neurons to compute the values, to the value on the right, which is just a blockwise operation. So you can actually just write down a matrix multiply. And this is a very important thing to actually do in your code, because not only is it simpler code to begin with, it actually allows you to take advantage of high performance implementations that use optimal data layouts, have improved cache coherency, and can automatically for you take advantage of special instructions such as SIMD, because on Intel CPUs you can actually push through like 4 floating point operations per cycle rather than just a single one if you were just to have a loop over the operations. One way to actually take advantage of this is to use what's called BLAST. This is a pretty common interface used in the high-performance computing area. And basically, it's a bunch of highly optimized functions for doing linear algebra. Just some examples would be like vector addition. There's a function called AXVY, matrix vector products, which is GEMV, matrix products, which are GEM-M. And there's a whole bunch of different implementations for this, for different architectures. You have Intel's version, Atlas. These are all on CPUs. Then on GPUs, you have cuBLAST, which is the CUDA version. You have ACC, and then OpenCL, which is CLBLAST. And these are actually used in a whole bunch of different neural network libraries under the hood to actually get good performance. Like NumPy uses these, Theano uses all of these. And they're just something to be aware of. If you're going to write your own code, you want to be using libraries like these. So the first two things, that's really just sort of a general idea of like computationally you want to be doing those things. More algorithmically, a different idea is actually to implement batching. So I know typically so far in class you've talked about evaluating these neural networks. You do the forward pass for a single sample, then you do the backward propagation to get the gradients, and then you would do something like gradient descent or adagrad to update your weights. And that's your learning process. Unfortunately, on a lot of architectures, the cost of calling for various operations is quite high, as well as you typically lose a lot of performance just in the amount of overhead between calling sort of more dense operations, such as your matrix multiplies. So what people tend to do is they use batching, and what this does is it's a similar idea to the blockwise operations where you took individual neurons and grouped those together into a block operation. But in this case, we actually take the block, like the neuron block from each sample, and we combine these together into a single block and then do a single operation over a bunch of different samples all at the same time. So for an example, you can see on the first equation here on the left, so we have another linear product. This would be in the case for a whole set of neurons, like an n-dimensional hidden unit. Now if we were to apply batching, we would actually pack both the y vector and the x vector into a matrix themselves, and here we're turning a matrix multiply into a matrix vector multiply into a matrix multiply, and this is actually much more computationally efficient. And then at the end of your forward pass, you have now, instead of the values for a single sample, you actually have the values for a bunch of samples. You would average the gradient that you get out of this and do your update based on that that average gradient. Unfortunately, one of the problems with this, well, actually, I should go over the benefits, is that, so yeah, doing this, you also get better cache coherency, because if you consider the first operation here, so this, the linear multiplier, or the linear product, when you are applying this to multiple values, you actually only have to load the coefficients matrix you once. So you get away, or you reduce the total number of memory loads. So if you were to do it individually for each sample, you'd have to load A from memory for every single sample. for when you're doing in batching, you only have to load it once, so you actually save a lot on your memory access. I know these are a lot of low-level details, but they actually give you a big performance improvement. You can get factors of, yeah.
Can you define cache coherency?
Oh, so cache coherency is in a modern microprocessor, you have so you have your memory, and then you have a processor sitting on top of that. The time for your processor to actually access your memory is actually really slow. Your memory is a really slow thing. So what they do is they stick in between this cache, which is like a temporary high-speed version of memory, which is very small and can store little chunks of your memory that you're operating on. So if you're only working on a bit of what you have in memory, you'll load it into cache and be able to work on that at a much higher speed. But what cache coherency means is that because that cache is so much smaller than your memory, it can't fit all your working data in there. So if you have an algorithm that needs data from all over memory, you're not going to do very well, because your cache is going to be, you're going to be removing what you had in cache to load new things from memory, and so you're not going to have this ability to reuse what you already had in cache. So that's sort of the fundamental idea behind cache coherency, is to exploit this multi-tiered memory hierarchy to reduce your costs to access main memory. Okay, so yeah, so you have cache coherency, and then you have less function call overhead. Unfortunately, when you go to batching, you actually have worse convergence in terms of applying your stochastic gradient descent algorithm. So as you increase your batch size, even though you're processing more samples per second, it'll actually take more iterations to converge to the optimal solution. And another issue with this, particularly in natural language processing, is that depending on the sample, the topology or the architecture of your network can change. So applying batching or how you apply the batching isn't immediately obvious, because for certain hidden units, you might not have the same number of samples to evaluate the activities for, because you might have a different parse tree, or your sentence might be a different length, for example. So batching is a great thing, but it can be difficult to implement depending on your model. It's something you have to look into. Okay, so now that we've done a great job of implementing our code just for a single thread, let's see how we can actually use GPUs to speed it up. So just a bit of an idea about GPUs versus CPUs and way there. So a CPU is typically, it's a high frequency. So it executes many clock cycles per second, but has a small number of cores. So every core can do like a fixed number of operations per second at the rate that your CPU is operating at. On the other hand, you have a GPU, which operates at a lower frequency, but it has way more cores. So if you do the math in terms of the number of floating point operations you can get through on GPUs, it's actually much higher. So for the latest Intel CPU, so down on the left here, you can see the peak performance is about 238 gigaflops. So that's floating point operations per second. While on the latest NVIDIA GPUs, you get about about 20 times that in terms of your floating point operations, as well as you get higher memory bandwidth. So the memory bandwidth, what that means is, when we're talking about cache coherency, that's the speed at which the CPU can get data from your main memory. At least for the CPU. And for the GPU, because you have memory on board, it's the rate at which your processors can get access to the memory on board on the GPU. So at first look, GPUs seem amazing, because they have a huge amount of floating point performance, as well as good memory access performance. However, there's a bunch of caveats that you have to take into account when you're looking at them. So one of the things about GPUs is that they actually have very limited memory capacity compared to CPUs, which for a lot of problems isn't a big deal. But if you actually need more memory than is on your GPU, going from your GPU to access main memory on the computer, which you generally have way more of, to access different weights or different samples, for example, this can actually be very slow. Typically in GPU servers right now, to actually have a GPU access your main memory can only operate at about a maximum rate of about 16 gigabytes per second, which can seriously hurt your performance. And the thing is, we were talking about how GPUs are amazing. Yeah, they have great floating point performance, but compared to CPUs can actually access your main memory at about 100 gigabytes per second. So now you see this, it's like, maybe it's not going to be faster in the end. There's going to be a trade-off there. So that's something to consider. Another thing is the programming model for GPUs is a bit different. You have to rewrite a bit of your code to figure out how to map it to it. Because things like reductions and barriers are a bit of an issue. And what I mean by barriers, like if you do a matrix multiply, at the end of that you have to wait for all of the processors on the GPU to be finished computing in order to have the final results from that. Other things are slow, like reduction. So if you're doing a dot product, so this is like an all-to-one computation. Sure?
You said the GPU memory is small, so does this mean the batch sizes are going to be smaller?
Yeah, I mean, it depends. For in our computer vision code, that was definitely a limitation, but the data you store for most of the NLP systems is quite a bit smaller, so it's not as big an issue. Right, so reductions are slow, so these are all-to-one communications, so dot products or minimums or maximums over vectors, as well as the kernel launch. So the kernel is just a term for a small bit of code you send to the GPU with a bunch of data to run. And typically you would call initiate kernels from your CPU code. So just to give you an idea of some of our experiences working with GPUs, just implementing a simple RNN model, we experienced like two different sort of cases. When we were using about a hidden state of about 100 dimensions, we actually found CPUs were faster. And this is due to less overhead, better memory bandwidth.
Recurrent neural net?
Yeah, exactly. And this is because our matrices and basically your linear operations are your fundamental building block of all these neural networks, and you apply nonlinearities. So the big thing is these 100 by 100 weight matrices, these coefficient matrices you have in these systems. And if you have to shift that around, that's quite expensive. So we found that GPUs were approximately 2 times slower when you had a hidden state of 100 dimensions. However, when we went to a hidden state of about 1,000 dimensions, we found that GPUs were actually much better than CPUs. And this is just due to the raw floating point performance that you can get out of these things. So when you have a hidden state of about 1,000 dimensions, your matrices are now 1,000 by 1,000. So this is, if you want to do a matrix vector multiply, you have 1,000 times the floating point operation, or 100 times the floating point operations you have to perform. And GPUs, simply because they have 20 times the floating point computational power, they're going to beat a CPU. I mean, that's just the truth. And so in this case, we found that GPUs were about 10 times faster than CPUs. Unfortunately, even no matter what you're doing, if you're working with CPUs or GPUs, at some point you're going to hit a limit simply because staying within a shared memory environment or using just a single GPU or a single CPU is going to be the bottleneck. You're going to just max out the floating point operations available.
Just a quick question about the previous slide.
Yeah.
So what do you mean by, why are the matrices being passed around? Do you mean like between main memory and GPU memory?
Even just on cache on the GPU.
I see.
Yeah.
I see. It sort of seems like it's small enough that it was, I don't know. Maybe.
But I mean, it was other things. It just overhead, like function call overhead, like spawning off the kernels can be really expensive on GPUs too. And you ultimately have to copy your sample data over to the GPU, and that's, even though it might not seem too big, the cost of incurring that call to go through like the CUDA driver and then actually have that spin up the system calls to have it ship the data from main memory can be quite expensive. So if you run a profiler on this, you'll just see it. Your kernel will execute, then it will spend for like 1 millisecond, then it'll spend like 10 milliseconds just sitting there, and then it'll do work for another millisecond, and that's the kind of performance you're going to see. Because it's simply, we don't have the bandwidth between your CPU, which does sort of all the, like the controlling of what the GPU is doing, and the GPU for actually doing the processing. Okay, so yeah, we basically figured out CPUs and GPUs, they're great for different applications, but ultimately we want to go parallel because that's how we're going to scale up these systems to solve, rather than to solve things faster. So we don't want to be stuck generating a translation model over 10 days because we're going to have more data, a more complicated model, and it's just going to be slower as time goes on. So we need to exploit parallel processing. So this means even clusters or even the cloud. So that's our goal now. So just to give you an idea of how, or the basic idea, or the simplest idea for implementing parallelism in a neural network model, is consider we have a model and a number of workers that we can work with. This could be a bunch of different CPUs or a bunch of different GPUs, whatever architecture you have. You can think about it abstractly at this point. So the first step is we distribute like a sample to each of our workers. It could be the data, or it could just be the index and have the workers read the samples for themselves. It doesn't really matter. I mean, it depends on the particular application. Then at each worker, we compute the gradient separately. So we do the full forward and backward propagation on each worker separately for a separate example. And then back on the master, so this is like the main thread, we go and we average out these samples and use them for the update. So in some ways, this is actually very similar to the batching that we were talking about earlier, but in this case now each sample is, the forward and backward propagation for each sample is on a different computational node. And as it turns out, this is really efficient for a lot of things. And it's super easy to implement basically for any model that you have. I mean, one of the problems that comes up is that if for each sample the model complexity is very different, you're going to get a lot of, if the computational time for each sample on each worker is very different, you're going to waste a bunch of time waiting for all your workers to be done. But in a lot of cases, it still helps you a lot. Unfortunately, you suffer from the same problems as batching. After a certain size, so a certain amount of parallelism, your effectiveness in terms of solving the optimization problem goes down. So the next idea is actually model parallelism, and this is where it gets a bit more interesting. So the general idea in model parallelism is to take your computational graph and actually partition it based upon the data dependencies. And once you've done that, you can distribute the different parts of your graph to different computational units. And then go ahead, do your forward and backward propagation for a single sample, but you've partitioned it, and exchange the activations during the forward and backward passes, and also the gradients if weights are shared. So let's look at an RNTN. Here we have the tree structure. This is just one off the top of the website. I'm sure you've all seen it. Here's one sort of simple partitioning or partition that we could come up with, where we partition sort of the two main subtrees of the model into the two lower subtrees, and then we have the root tree at the top. So the first step here would be to take these two lower trees here. We evaluate each tree independently on two different workers to compute the activations given the weights and the data for a single sample. We can send these to the third worker, which would be responsible for the root tree. Then we can compute the activation at the root tree, given the activations of the subtree as well as the data if it needs it, whatever the expression is. And that's done. That's all there is to model parallelism for the RNTN. And then backwards propagation would just be done in reverse. On the worker 3, you would compute the deltas and the gradient, or the components of the gradients due to that part of the tree, and then you would send the deltas back to the workers, and then they would compute the parts of the gradients that are due to those parts of the subtrees. So another example is convolutional neural networks. The previous example, RNTNs, this was an unstructured graph. So when I was talking about unstructured before, that was a very good example. And you could see from that, actually how to partition it isn't necessarily the most clear problem. Alternatively, we have CNNs. These are nice and structured. And so, I mean, that's the reason why I chose them, because we can show that once you have a structured problem, it's actually much easier to parallelize it. So partitioning it is fairly obvious. In this case, we partitioned it into 3 different chunks here. And now, to do the computation, it's also simpler. So in this case, we have, let's say we want to compute the neuronal activations for the three neurons in the center partition at the second level. Well, it needs 5 bits of information. So in this case, it would use the values that we stored locally, as well as 2 values which we grabbed from the neighboring partitions. And you can see what it's doing here. It's exploiting the spatial locality of the structured data. And so, once again, you can do the forward prop back like this, and then on the backwards prop, it's a similar pattern where you're exchanging information at the boundaries of your partitions. Here's another example, recurrent neural networks. So when you look at this, it might not be immediately obviously how to parallelize this, but it's, once again, you can actually do it. So in here we have a 3-layer recurrent neural network. I mean, it could be any variety of different recurrent neural networks. It could be an LSTM. It could be our GRU recurrent neural network. And normally when you're computing this, you would just evaluate the values at the first hidden unit at time -1, the second hidden unit, or the hidden unit at the second layer at time -1, etc. And then move on to the next time step, and you would just work in lockstep like that. But there's actually a trick to computing this in parallel. So the first step is you do partition it among your workers based upon the layers. So you assign each layer of your RNN to a different worker. And then you actually compute on the diagonal. So in this case, we actually evaluate the first hidden unit of time -1 in the first step like this. Then we actually can evaluate the next two hidden units on this diagonal like this, the next step, and so forth. So here's the third step. And the thing is, these are all data independent. So these can be done independently on your different workers, whether different CPUs or different GPUs, and you're only exchanging your hidden state between these, not any larger vectors. You don't need to exchange your weights necessarily if the weights aren't shared. So step 4, step 5, and step 6. Okay, so we've talked about two different forms of parallelism in terms of how you can distribute your model, both in terms of data parallelism, where we evaluate our architecture independently on each different worker for a particular sample, or where we have model parallelism, where we actually subdivide the computational graph for the model. Just to recap, the pros for data parallelism is that it's really simple. You can pretty much apply it to any model, and it's fast when the weights are small and sparse, because ultimately you need to exchange the gradients that you computed for the model between all of the workers. Unfortunately, if the weights are large, which can be the case in some models, this is actually prohibitively expensive. On the other hand, model parallelism can be really great. It's more flexible. It can avoid the large batch problem. You're actually getting parallelism without increasing your batch size and degrading your stochastic gradient descent performance. And it can also handle larger weight sizes if the weights aren't shared between the partitions of the model. Some of the cons, it can be slow if the activations that need to be exchanged are large, which, once again, this is very problem dependent. And it can be really complicated to implement. And it's one of the other things is that it's not necessarily clear how to apply model parallelism to certain models. Another thing to consider is shared memory parallelism. So here's another thing to think about. Just examples of what I mean by shared memory parallelism is when you have a machine with multi-core CPUs, or if you have a single GPU card, because this is an isolated chunk of memory that you're working with. Unfortunately, even though you can parallelize on these, you have limited scalability. The largest machines are still 64 cores. GPUs are 5,000 cores, so it's still not great. We want to move beyond that. So we want to go to distributed memory parallelism. So if you take the previous models and you can distribute them in parallel across different computational nodes. So there's some things to be aware of as you're doing that. If you have multiple machines, so this is when you're distributing your neural network across multiple different computational nodes in more classical high-performance computing cluster. One of the really important things is to realize that the communication time between these boxes is very slow. On many clusters, we have gigabit Ethernet, and this is about 128 megabytes a second. So if you have weights that are in the order of hundreds of megabytes, or even gigabytes if you have a large set of word vectors that you need to exchange every single time, for example, like data parallelism, this can make an iteration where the cost to do the computation takes like a fraction of a second, can take multiple seconds just to do the data exchange. So in order to make it work in these scenarios, you need 10 gigabit Ethernet or InfiniBand, so where you can get gigabits a second or gigabytes a second in terms of your exchange rate. If you're looking into multiple GPUs in a single box, these are a lot better in terms of communication, because you can use the device-to-device communication along the PCI Express bus, and you can get 16 gigabytes a second pretty easily. Once again, you're pretty much limited to the number of cards you have in a computer, to about eight GPUs. one of the things to realize, so yeah, I said we can have fast communication between the GPUs in the same machine. But what we found, surprisingly, when we were setting up our own systems, is that we bought these 8 GPU card systems, and the communication between the first 4 was fast and the second 4 was fast, but in between those 2 sets of 4, because of the architecture of the PCI Express bus, it was actually quite slow. So we were back at the same problem of having like multiple machines where communication was down to hundreds of megabytes a second, which actually hurt our performance a great deal. So another thing to consider in distributed memory parallelism is to take advantage of both your GPUs and CPUs. So if you can have code that runs in both environments, you can actually take advantage of all your computational resources. So one of the limits of parallelism. In terms of data parallelism, batching stops helping at about 256 samples in a particular batch. It's problem dependent, but that's what we found for a lot of our problems. In terms of model parallelism, it's really limited depending upon the type of model, because it depends on how you can partition the model, you can partition the computational graph, as well as the amount of data that needs to be exchanged between the different partitions of your computational graph as you're doing the forward propagation and backward propagation. And a lot of these things also come down to Amdahl's law. So if you're a good computer scientist, you know about this. And what this says is that if you take a computer program and you can divide it into 2 parts. One part you can parallelize into an arbitrary number of computational units, and another part which actually has to be done in serial, you're actually limited in terms of the amount of performance improvement you can get. So if we were to take an algorithm that is 95% parallelizable, the maximum speed up you can get from going in parallel is about 20 times. Fortunately, actually, if you're doing batching, which is one of the great things about batching, is that you have about, you can actually, depending on your implementation, you can get pretty linear scaling, depending on how much data you have to exchange in the gradients at the end of the batch. One of the things I'm going to talk about is asynchronous stochastic gradient descent. So this is a new technique that people are using to avoid some of the issues that people have had with parallel implementations before. So in a typical, let's say, data parallel situation, you do your forward and backward propagation for each sample, and then accumulate the gradients, and then distribute the updated weights to all the workers. Unfortunately, because the amount of work that you're doing is different on each of these on the workers, you're actually going to waste a lot of flops while some workers are unfinished. And on top of that, you're going to waste a lot of time exchanging data between the workers and the master, or workers and other workers when you're exchanging gradients. And so the amount of time you're actually spending on any particular computational node actually doing computation can actually degrade very quickly. So what people did is they introduced an asynchronous loop into the mix. So what this means is that on each worker, you run a separate loop, which in a separate thread, which what it does is it grabs it grabs the data, it does the forwards and backwards propagation, it updates the weights locally using the local gradient, and then just continues onwards without locking. So what you would do, instead of sending the weights back and forth and doing this all barrier where you're summing up the weights into an average and then applying them in a single update, you just apply each update separately to the weights and continue independently. And what this means actually is that workers can update weights while other workers are reading from the weights. And it's been shown empirically that this doesn't actually hurt convergence. In fact, it helps convergence at a lot of times. And you're not wasting a lot of computational time. So that in certain cases, people actually, compared to a data parallel system where you're locking to an asynchronous data parallel system, you can get performance improvements of 10 to 100 times because you're not waiting around for communication and for other samples to finish processing. So we're just going to go over a simple diagram of how this works, asynchronous gradient descent. So once again, this looks like the standard data parallel model. We have, in this case, instead of getting work from the master, each worker is just working on a single, like a shard of your data independently, computing the gradients. Let's say one worker actually finishes, it computes a gradient, computes an update to the weights, it sends this to the master computes the update, sends the updated weights to all the workers. The workers are continuing to process new samples and compute new gradients. Let's say the next one finishes. Well, it sends its weight update to the master, and the same thing happens again. And what can actually end up happening is that all these things start happening asynchronously, so they all happen at the same time. So one can be sending a weight update, the other one's going to be receiving a weight update, and this is the general idea behind asynchronous gradient descent, where we're not waiting for certain workers to be done computing gradients. We go ahead, update the gradients, and send out the most recent gradients to other workers. So here's another step. So yeah, ultimately everything happens at the same time. There's several variants of this. Google has their disbelief system. If you, that's definitely a paper that's worth reading. They'll give you another explanation of this. I mean, they're each different variants. There's Hog Wild, that's another one. And in these papers, they'll talk about different ideas. So one of the ideas is to combine model parallelism and data parallelism in the same paper. Or in the same model or in the same system. Because often you'll have different stages in your model where different types of parallelism will actually do better. So if in one stage of your model you actually are exchanging you have a bunch of shared weights and you need to exchange these and the weights can be large, it's better to use data parallelism. If in some parts of your model you have huge numbers of activations but a small number of weights, model parallelism could be good, so you can actually use different types of parallelism within the model. And in terms of the asynchronous gradient descent, if you want to scale this up from 10 to 100 to 1,000 workers, you can use a hierarchy of masters to coordinate a large number of workers. This is something that has been very successful in the disbelief algorithm. So just a couple things to talk about. So in terms of implementation details, one of the great things that people should use when you're writing high-performance code is to use automatic differentiation. So in automatic differentiation, what you do is you symbolically define your forward propagation. If you've used Theano, this is how it works. Once you've done symbolically defined your forward propagation, it can do the forward propagation, and then the library automatically computes the backwards derivatives. And the way that it does this is basically that your forward propagation, since you're defining it symbolically, all these operations that you've defined symbolically within the code, they predefined all the gradients. So they can just string them together using the chain rule into your backwards derivatives. One of the great things about automatic differentiation is that it greatly reduces bugs and debugging time. So this allows for more experimentation. You can try new models and different variants. There's a lot of great open source libraries for these things out there, Theano, Torch. Unfortunately, it's still not flexible enough or optimal for a lot of tasks. When you're using these libraries, they make you use a very specific model for defining operations, which can be difficult, as well as limit your ability to use parallel systems. Because although Theano and Torch, they work on GPUs, if you want to run on multiple GPUs, it becomes more complicated. Some of the research directions that people are looking into now. So one of the things is how can we actually change the model itself to improve the computational aspects? So the big theme of this talk, or what I've been talking about, is how to exploit a structure in terms of improving your computational efficiency. So how can we change our model to be more structured? So using more CNN type models instead of parse tree based models. That's one of the things that can be exploited. The other thing is to make your models wider rather than deeper, so use larger hidden unit dimensions. This allows you to increase model parallelism, and if your model is deeper, avoids a lot of the data dependencies that you would have had in the past. We can also modify a model's numerical properties. So one of the recent papers to come out for, I think it was Google's most recent ImageNet score, they used something called batch normalization. And the idea here is that in our neural network, since we have these nonlinearities, are actually saturating nonlinearities, what happens for a lot of samples is that as you're propagating the activations through the network, you actually end up saturating a lot of your nonlinearities. And so when you're doing your backwards propagation, the derivatives are going to be very small. And so you end up with a vanishing gradient problem. And this actually makes your optimization algorithm take far more iterations to converge. So what they did in that paper is they actually learn a mean and standard deviation to shift the activation after each layer or each stage in your neural network, such that the mean and standard deviation of your activations is centered around the linear part of your nonlinearity. So this forces your gradients essentially to not become zero, not vanish, as you're doing your backward propagation. And the other thing is just to search for better optimization methods. In the back of people's minds, there's always second order optimization schemes. How can we use those? Because those introduce more opportunities for producing faster code. You can get more dense matrix multiplies in terms of computing your gradients and your update vectors, as well as looking into communication reducing algorithms. So implementing a optimization algorithms that don't necessarily need to send gradients around. They can essentially independently look for the optimal solution, and then you go ahead and combine that optimal solution later on without exchanging gradients. So you can reduce the number of times you actually need to exchange information. And so that's my talk. Any questions? I knew I went quickly over stuff, so yeah, please.
Wait, could you go back to the first?
Yeah, sure.
Yeah, wait, could you like elaborate a little bit more on the batch normalization?
So yeah, I mean, I'd have to look at the paper, but I mean, the idea is essentially to combat the vanishing gradient problem. Do you know what that is?
Yeah.
Did you go over that in class? So if you can, between each set of hidden units, you insert a scaling and a constant offset, you can, if you know what the mean and standard deviation of your activations are, you can actually center those activations around the linear part of your nonlinearity, right? So if you're looking at like a 10H nonlinearity, if your activations are between like -1 and 1, the gradient that you're going to be propagating back through that in the backward propagation is going to be larger. It's not going to be 0 all the time, right? So that's the general idea of what you're trying to achieve with that.
Okay, so this is alternative to just using like ReLU.
Yeah, exactly. Yeah. Any other questions? Oh, sure.
Can you talk about batching in the context of some of the more complex networks like the parse tree based?
So I mean, yeah, that's one of the things that's problematic is, so yeah, you have different parse trees for every sentence. So I mean, if you just count up the number of hidden units you need to solve for, it's going to be different. So
Are there any tricks?
so I mean, there's stuff that I haven't implemented. There's ideas out there that people have implemented where basically you can group together. So if let's say if we have you can group together the evaluation of hidden units. So if you were to compute an order that you evaluate all the hidden units for a given parse tree in, you could start combining these in terms of combining the computations of different hidden units from different samples in your batch. Do you see what I mean? Okay, so you know, sir. Okay, cool. So, I mean, if you were, is this good to write on? Okay, it's on a chalkboard. Okay, so if we were to have like a graph that looks something like this, and something that looks more, let's say, for example, let's just make it one-sided like this. So if you wanted to evaluate it in a certain order, you could do something like this: 1, 2, 3, 4, 5. Right? You could evaluate this in this order and get the right answer out of your forward propagation. Similar over here, you could do something like 1, 2, 3, 4. So what you can do is you can actually evaluate this and this together at the same time, and that's how you would batch that. At a certain point, you're going to end up with like if you were to combine 1, 1, 2, 2, 3, 3, 4, 4, you could combine those all in parallel, but you would end up with 5 being in this graph being computed without anything being computed over here. So that's one of the things that you would have to do there. If you're doing a recurrent neural network, you could stagger the computation of different samples within your batch as well. Does that make sense? Okay.
The other thing you could do is like parallelize inside one batch and just compute, 500 or 200 trees at the same time. Each worker gets, 1 over number of workers or something, times the total. And then on average, each worker will have roughly similar
That's true.
lengths of trees and complexities of trees.
Yeah. So essentially, I think the term for that is over-prescribing. So basically, yeah, you're relying upon the average number of hidden units that you distribute to each of your workers to be the same. Yeah. Okay, go on.
Can I ask a question about argument?
Sure.
Say during machine translation, the next word depends on the previous word. And sometimes we use beam size. And
So this is during training when performance is really critical, and you know all the words and all of that information beforehand.
well, when doing project, we are doing inference, but during inference time, we have to do a beam size of 20 or 30. We're implementing the neural talk
Yeah.
to capture the problem.
So
That really slows the whole process. Is there a way to make beam searching faster here? So is it like a bottleneck that acts as a serial part?
so you're asking basically how you can parallelize beam search for machine translation, right?
Yeah.
I mean, you can turn it into you can batch it. I mean, that's one thing. You can actually combine all those operations. I mean, at each evaluation time, I mean, you can parallelize across all your beams at that point. But I mean, that's
Sure. Can I ask another question, maybe more related? So we talk about data parallelism and model parallelism.
Yeah.
So could you draw like a graph hierarchically? How can we combine them together?
what do you mean exactly?
Model parallelism and the data parallelism.
Okay, so if
So some of them share the model. Some of the model only exist in certain machines. In model parallelism and in data parallelism, they all share the same track.
so it really depends on your weights. So if you
So which one go as the first hierarchy?
So all it means is that, let's say, yeah, sure, why not? Oh, that's not great. Okay, whatever, we can just use this. So I know that in the work that we've dealt with, so I mean, just consider this. Imagine we have even just a linear set of these things where these things have like a hidden state that's like 1,000 wide or something like that, right? So you could actually you could split this node into 2 computations where you compute the activations for each like 500 of the hidden units separately on 2 different computational units, right? So you could do those separately, and then depending if, and the reason to do that there is, let's say, actually you wouldn't want to say more active. Yeah, it depends on your trade-off between the number of weights and the number of activations you have. So yeah, you would have, let's see.
Are you drawing the parameter?
Yeah, here, let me think about this. The context I've seen this used in is more like computer vision, and there's a pretty obvious example there. But the idea is that if the computation here involves a lot of weights, you want to do that in data parallel because, let's say for a matrix multiply, if you have a giant matrix like this, and you have a vector coming in, so we have another vector like this, and you do this multiply. Well, if we divide it like that, if we were to do this in data parallel, what you have to do is that this weights matrix here, so this is A, X, and Y like that. If we do this in data parallel, this means we have to exchange this entire A matrix, right? So if we do this instead, let's put that together, A2, A1, whatever. If we divide it like that, and we do this computation on worker 1 and worker 2 like this, where we take for like two examples. So this would be like x1 and then x2, and we for like the 2 samples in the batch. Then we don't actually need to exchange the weights anymore. So worker 1 would do the multiply between a1 and x1, and worker 2 would do the multiplication between a2 and x1 and a2 and x2. So the gradients wouldn't actually have to be exchanged between the 2 workers. And so the net amount of information you're exchanging is less. And so that's when you would use model parallelism. And really, it doesn't really matter upon the tree structure necessarily. I mean, that's not necessarily, it depends like on what level is the tree structure you're referring to. Like,
yeah, this is a good example of how model parallelism is better than data parallelism.
Yeah.
What about the other side? When does data parallelism win over the model parallelism?
so data parallelism typically wins, for example, in terms of, let's say if you have a convolutional neural network, right? And the number of channels you have is really large. Because the weights are really small, because of it's a convolution, right? So your weights are all shared everywhere. The amount of information you're exchanging, the activations can be vastly larger than the weight parameters themselves. Does that make sense? Okay.
Small filters, but larger.
Yeah. Okay.
Are you just able to say anything more specific about the like this second order optimization methods, like which ones might be especially amenable to the parallelism?
No, I mean that's just. I mean, I have a couple ideas, but nothing concrete. Sure. Sure.
A couple of areas that seem like that I haven't like seen directly applied to like deep learning models.
Yeah.
I'm just kind of curious if you have any thoughts on whether they're applicable. One is like approximate computing, like performing floating point operations with like some margin for error, but faster. And then secondly is this trend of CPU-based coprocessors like Intel Xeon Phi.
Yeah. Okay, so for the first question, I mean, the one thing that I know people are doing are working with lower bit count, lower precision floating point numbers. And I know there was at least one paper that got it down to 12 bits, and accuracy did go down slightly, but it still worked. I know certainly you don't need to run it in doubles, and you can pretty much get a 2 times performance improvement just switching to floats. Like, what other ways would you reduce the accuracy? Are you thinking about?
No, yeah, just reducing the bit count is all I was saying.
Yeah, so you can definitely do that. I mean, certainly don't run in doubles. Just run in floats. I mean, you can use doubles for like your gradient checks and stuff like that, but definitely during production, during training of a real model, you can use floats. As far as using like 16-bit, I mean, you're welcome to use that as well, and it will work, and it'll probably be just as accurate. But I mean, you'd have to write extra code. It's not as easy to write that. Sorry, what was your second question?
CPU-based coprocessors.
Oh, CPU-based coprocessors. So, I mean, Xeon Phi pretty much, in a lot of ways, is like a GPU. So, you're still stuck with a lot of the issues in terms of your limited memory.
But you have a big instruction set, right? Because it's like general purpose.
Yeah. That's the thing. So we haven't tried it. I haven't tried it myself. I suspect that for NLP, it may be better for like this. So the case we were looking at before, where we had a hidden dimension size of about 100. I suspect it would probably be better in that case than GPUs. But I mean, once you're up to a really large matrix size, I mean, I think that just having the raw floating point performance is where you're going to do best. Does that make sense? Okay. Any other questions? Cool.
Do you know any work with FPGAs and neural networks?
Yeah, there are definitely a few companies interested in doing that. I don't really know the shtick on that. Do you know?
I mean, it seems like it's sort of for very specific architectures. If you know exactly, that convolutional neural network that you want to implement and nothing else, and you want that to be as efficient as possible, and your instruction set really only you really only need to do all the operations that CNN requires, then, and it's like, especially for embedded devices, it's useful.
So it seems like a deployment.
Yeah, I think for embedded devices, if you wanted to make your phone have some really fancy algorithm and you didn't have an internet connection to go to the cloud to just use some off-the-shelf hardware, I think that's definitely what you're going to have to do to a certain extent. I mean, GPUs and phones and stuff like that are getting better, but I mean, there's no beating the performance of dedicated hardware to these types of things.
From you guys' perspective, do you think that's going to be a trend, or do you think the trend's going to be kind of going off to the cluster and getting results back?
It's unclear.
I mean, at this point, we're just kind of postulating what may or may not happen in the future. It's clear that if you can run stuff on your device, it's a huge advantage.
Yeah.
At the same time, the larger the model, even just like, let's say you have the simplest model, like just image in and one softmax on it, but now you have 80,000 classes. That single matrix multiplication is kind of, even if you could do it on the phone in terms of speed, it will drain the battery.
Yeah.
And right now, there's just no way you couldn't drain the battery with that kind of large computation. So it's unclear with current battery performance and so on that is something you'd want to train very large models on. That being said, for very small numbers of classes, right, like you need to only find like faces only or something like that. That is certainly doable on device.
But that's where FPGAs would come in. Like they'd be way more power efficient than your cards.
There's a company called TerraD.
Yeah.
Like and they implemented AlexNet into an FPGA.
Yeah.
And it like is really is not power hungry really at all. But again, like we were saying, is task dependent.
Yeah.
Right. So I guess you can put the first few layers.
Because implementing a convolution in hardware, it's like the best possible thing you could ever implement in hardware. So yeah, I'm not surprised by that at all. Go ahead.
Like you said, that model parallelism can be like very due for different kinds of models. Like for Arduino, you might want something like a diagonal parallelism or something.
Yeah.
So do these several like off-the-shelf packages like Piano or Torch all implement these sort of?
Off the top of my head, no. I don't think they do. I mean, we've had
So model parallelism is hard because you have to know what the model is, and then like Elliot said, right, there are different ways you could do it, and it's not like different automatic differentiation where if you know the forward function, you know for sure the backward function, right? It's like you still need to fiddle around with it. So for sure is.
It could be done since they're doing symbolic differentiation, they're building up a symbolic graph like that. If the graph itself could be partitioned, they could run a graph partitioner and do that. But the overhead of actually doing that on the fly is probably, because the individual computations are so efficient when you're using like a block structured multiplication library like BLAST or something like that, the cost of doing the unstructured computation to compute the graph partitioning for the parallelism might actually not win you anything.
Secondly, so these things are so inherently using lots of BLAST routines and all. And so BLAST routines themselves can be parallelized. And is that kind of parallelization also used, or? Yeah,
certainly. I mean, BLAST can use like SIMD. I mean, we use cuBLAST on GPUs. I mean, we write our own kernels, but I mean, we're not going to beat the hardware people at NVIDIA writing their own BLAST. So we might as well just use the library. Yeah. Sure. You had a question?
Yeah, I just kind of have like a more basic question. Like,
sure.
I guess choosing between like Piano and like Torch, are there any significant like advantages to like choosing either? You're probably starting the project.
So I have only limited experience with Piano. I've looked into Torch as well. My understanding is that Torch is more flexible in terms of what you can do. but they're still missing features in terms of parallels. I mean, neither of them has like a distributed version like disbelief built into it or anything like that. If you're interested in that.
I think it largely depends on what language you're familiar with at this point.
Yeah.
In your particular production environment, but just like more generally in a production environment, is it still a win to, I guess you sort of already suggested this, but to do like basically C++ as opposed to some higher level language because of the detail, especially I guess because of the details of parallelism?
There's various reasons beyond just the math, but just software engineering reasons why a strongly typed language is better for production. We found it works really well in production actually, and we've had a lot of success handling a lot of throughput without things failing that way. Yeah.
I don't know if it's beyond scope, but do you have some experience building a GPU machine, like what parts is good, or what do you think of the configuration of NVIDIA digit stack box? How much memory, how many sockets, what kind of CPU?
It depends what you're doing. I mean, honestly, yeah. So if you can use the GPUs effectively, yeah, having more of them is great. But it's also a waste if you can't do it. I mean, if you just have something that runs in a single GPU too. In terms of memory on the computer, I don't know. It depends on what you're going to do. Are you storing like a large amount of data in memory, like you're reading everything off disk and just storing it in memory? Is that something you need to do, or I mean, it depends on your application. I mean, for us, it still actually matters having fast CPUs because you still end up doing a bunch of computation on the CPU. Particularly, one thing that we did was you push like all the data loadings into a separate thread, so that as soon as you can do the computation on the CPU, you have the data ready in memory to copy. Stuff like that. Any pre-processing we do on the CPU.
So comparison between the Xeon E5 cores or the desktop, the Core i7 cores?
Yeah, I don't have any. We haven't run any of our code on the Xeon Phi. Actually, we're interested in doing that, but we haven't done it yet. It would be a good comparison to run because it is a different architecture that has certain possibilities for these types of networks. Yeah.
So in terms of your question on the programming language, it also depends on, do you want to have a production environment or you just want to iterate quickly through some models. So it's a lot of work to create your own C++ framework in which you can then iterate very quickly. Such that, I just put this kind of node together with this kind of node, and then add some bytes from here and maybe some recurrence there. That is a lot of work if you want to build a robust C++ framework that allows you to so quickly put together a new model. Whereas in Theano, you can just very quickly put something like that together, try to run some experiments, and in terms of the class project, that is probably what you want to do because you have limited time. You can't build this abstract general framework that could, in theory, then create tons of, basically all the Lego pieces we covered in class, have a super great software engineering. In the end, you don't run enough experiments for your project by the deadlines.
Yeah.
So just one question. So suppose that at the end of it, also suppose that I just wrote something like a NumPy code that runs on like GPU using something like gnumpy or something versus writing my own maybe CUDA version of the code. Like how much faster is like speed difference?
So I honestly don't have a great answer for you. NumPy is, in terms of the actual operations, it's pretty close to optimal. But if you start interacting with those numbers in Python, that's when you take a big performance hit. So if you can avoid doing that, then it's pretty good. Sure.
Do Piano and Torsional work with both CPUs and GPUs, or just CPUs?
They work with both. Yeah. Because I think it's, if you're using things like BLAS and you have an abstract data container, which is what you have essentially in both, you can switch between the two modes pretty transparently. Which is nice because it lets you see which is actually faster. You can turn one off and just do a comparison yourself. Yeah.
Which is also something you can implement in C++, but again, it'll take a long time.
Cool. Any other questions?
All right, let's thank our visiting speaker.